Good morning, students. Greetings from the Department of ECE, SJBIT. So today we will look at the proof of S parameter properties like unitary property and reciprocity property proof. So already we had discussed about the phase shift property and square matrix, the properties of S parameters, like 5 properties you have: the phase shift property, and S matrix is a square matrix which is of order n cross n, S indicating scattering parameters. And S matrix will, the diagonal components in the S matrix will become 0 for a matched network. And reciprocity theorem, it says that Sij, which is equal to Sji under the condition I not equals to j. So that means S12 is equal to S21. And last property which we have is a unitary property. So indicating that S conjugate transpose must be equals to S conjugate transpose must multiplied with S matrix, which must result in unity. Or otherwise you can say that in any given S matrix, the square of elements multiplied square of elements, sum of the square of elements either row wise or column wise, if you it must be equals to identity. So today we will see the proof of unitary property. So for that, so proof of unitary property, we need to prove that S conjugate transpose must be equals to identity matrix. Proof of S unitary property. So for that we will consider a two-port network which is lossless. So we know that for a lossless network it satisfies the unitary property, and for a reciprocal property for a symmetric network it satisfies the reciprocity property. Okay, the proof of unitary property, if you observe, take a two-port network and assume that the network is lossless. So if the network is lossless, so it is a two-port network, and we know that A's and B's, which are representing the powers, incident wave and reflected wave. So A1 at port 1 and B1 representing the reflected one. This is a port 1, and consider this a port 2, and A2 is the one entering into the, A is indicating incoming wave and B is indicating outgoing wave function. And we are considering that according to the property, it says, according to property, it says for a lossless network, it satisfies S conjugate transpose multiplied with S must result in identity matrix or unity. Now we consider a lossless network in a two-port network, as we have considered. In a lossless network, there are no losses. In such cases, whatever you have means which has been entered, which has to be left out. That means you can say that power leaving must be equals to power entering. A is representing the power entry and B is representing the power leaving. Wave functions, power leaving must be equals to power entering. So in the two-port network we can observe B1 square plus B2 square represents the power leaving from the ports 1 and 2. Similarly, power entering into the port, which is represented as A1 square plus A2 square. And consider this as equation 1. Then we start proving this. Consider this as equation 1. And we know that from S matrix, B value which can be represented as B1 and B2 for a two-port network which I am considering. So for this, if I consider a B conjugate, so B conjugate means all the elements in the B matrix has to be conjugated, B1 conjugate multiplied with B2 conjugate. And consider B conjugate transpose of this, which will be, you need to transpose this, which gives you B1 conjugate, row column matrix will become row matrix now, B1 conjugate and B2 conjugate. So now we multiply B conjugate transpose multiplied with B matrix. We'll observe what will happen and what you will get. So B conjugate transpose, which we have got It is a row matrix which has B1 conjugate and B2 conjugate. And B matrix, as we know, it is a column matrix. It is having B1 and B2 as two components. So if you multiply these two, you will get first row and first column to be multiplied. So you will have B1 conjugate multiplied with B1. So obviously you will get this as B1 square. Reason, suppose if I have 2 plus J3 and conjugate of that will be 2 minus J3. If you multiply both, imaginary part will be cancelled, only the real part will be squared. So under that concept. So B1 square similar plus B2 square. So you can say that, consider this as equation 2. So B1 conjugate transpose multiplied with B conjugate transpose multiplied with B results in B1 square plus B2 square. Already we know that B1 square plus B2 square is the one power leaving from the two-port network. So substitute this equation into equation 2. So equation 2 substitute into equation 1. So which results in B1 square plus B2 square we have. You can also write that B1 square plus B2 square as B conjugate transpose multiplied with B conjugate transpose multiplied with the B, which results in B1 square plus B2 square. Similarly, the other side, you have A1 square plus A2 square. You can also write this as A conjugate transpose multiplied with A. So consider this as equation 3. And we know that in general, we can represent the S matrix as B equals to S into A. And take a transpose on both sides. If you take transpose on both sides of this equation, B transpose on both sides, if you consider, which results in B transpose. Once if you take a transpose for S into A multiplying matrices, order of the matrix will change. So which results in A transpose multiplied with S transpose. Order of the matrix has been changed. So now you take a conjugate of this on both sides. So if you take a conjugate on both sides, if you take conjugate on both sides, it results in B conjugate transpose, which is equal to A conjugate transpose multiplied with S conjugate transpose. So consider this as equation 4. Now you substitute this equation 4 into equation 3. So in equation 3 we have B conjugate transpose into B equals to A conjugate transpose into A. So now we are substituting in place of B conjugate transpose as this part. So now if I substitute equation 4 into equation 3, which results in, now you substitute, after substitution, A conjugate transpose multiplied with S conjugate transpose multiplied with B. B is nothing but S into A. So now you can substitute B for B as S into A. This is on left hand side. On the right hand side you have A conjugate transpose multiplied with A. So from this equation you can send all the terms to the one side and take common terms. So if I send this term to this side, which gives you A conjugate transpose multiplied with S conjugate transpose multiplied with S into A minus A conjugate transpose multiplied with A must result in 0. Among these, you can say that A conjugate transpose into A you can take common. So by taking A conjugate transpose into A as common, we will be left out with S conjugate transpose multiplied with S in this first term. Second term, total I have taken common. So we will be left out with identity I. So which is equal to 0. Now you consider this equation. If this equation has to become 0, either this term, product term has to become 0 or this term has to become 0. Either this must be 0 or this must be 0. So this you can't make it as 0. This you can't make it as 0. Reason for that is A is the incident wave. So once if you give an incident wave, then only you will have a reflection, means a term will never become equals to 0. Hence, you need to make the second term to be made 0 to satisfy the above equation. So, S conjugate transpose multiplied with S must be equal, minus I must be equals to 0. So, if I rewrite the expression which gives you S conjugate transpose multiplied with S must be equals to unity or identity matrix. So, for a lossless network, we have proved that S conjugate transpose must be equals to, multiplied with S must be equals to identity matrix. In the same manner, this is about the proof of unitary property. So, now we will consider the proof of symmetry property. We'll look at proof of symmetry property. Symmetry property, according to that, it says Sij must be equals to Sji. So, symmetry property, which is for a lossless reciprocal network of a reciprocal network. Interchanged meaning is you can interchange the ports. So, proof of a reciprocal network, symmetry property of a reciprocal network. So, a reciprocal device, we know that it has the same transmission characteristics in either direction of a pair of ports, and which is characterized by the symmetric matrix, scattering matrix, which is given as Sij must be equals to Sji under the condition I not equals to j, where I not equals to j. This condition, which also results in S transpose, must be same as S. So, we will consider this as equation 1. So, this is according to the property. According to the property, it says for a reciprocal device, it has the same transmission characteristics in either direction. Okay. So, now we will prove this one. So, to prove this, we start with the steady state voltages and currents and the normalized values. So, we know that the steady state currents and voltages, which are represented as